Hello everyone, and I hope you're all doing really well and ready for some more National 5 chemistry. Today we're going to be talking about the energy released from fuels and when we burn different fuels and how we can set up an experiment to measure the energy released from fuels, and then we'll also look at a calculation involved with actually calculating specifically how many kilojoules are released when we burn a certain amount of fuel. So here's an example of the experimental setup that we would be expected to know for our National 5 chemistry exam in terms of how we could calculate and measure the energy released from burning a fuel. So if we look at the bottom of the diagram here, we've got our fuel, which is the alcohol methanol, and a little spirit burner, and we are combusting the methanol, reacting with oxygen, and it's producing heat. There's a little flame there. Now, what we can do is we can measure that heat energy produced and then calculate how much energy is in the methanol. So how would we do that? Well, here's the setup at the top of the experiment, which captures the heat energy and allows us to measure it and quantify it. So essentially we have a beaker. Now this beaker must be made of an appropriate material, something like copper, which is a good conductor of heat. We wouldn't use a plastic beaker or an insulated beaker here. We'd want to try and use as good a conductor as possible, and copper's a pretty good one. There are better ones, like a gold beaker would be better, or a platinum beaker, or even a silver beaker would be better than copper, but for obvious monetary reasons, copper is a good substitute for those ones. Into the copper beaker we have a known volume of water, something maybe like 250 centimeters cubed, 200 centimeters cubed. However much it is, we need to know the volume of water in the beaker. And we've also got a thermometer which will measure the temperature of the water. Now essentially all we're doing is we're burning the methanol, heating up the water, and then measuring the temperature increase. And essentially, if we know how much water is in the beaker and we know a number or a value for water called the specific heat capacity, what we'll talk about in a second, and we also know how the temperature increase of the water, let's say it's increased by 10 degrees, we can work and factor all those numbers together to figure out the energy released in kilojoules of methanol. There's a couple of things I want to also address while we're looking at this image. We also have something called a windshield, or sometimes referred to as a heat shield as well. Now this tries to keep as much of the heat energy within the experiment as possible. What we want to do is avoid any heat being lost to the surroundings. Ideally we want all of the heat energy from the methanol to be applied to the water. So that's why there's quite a close distance between the bottom of the copper can and the methanol flame. Should be really about 1 centimeter, no larger than that. So the kind of tip of the flame should be just under the bottom of the beaker. And also the thermometer should be set up exactly like this. This is a good placement of the thermometer because we are only interested in the temperature of the water, not the temperature of the copper can. If we just rested the thermometer at the bottom of the beaker, we would be measuring the temperature of the copper can and not the water. So this is the general experimental setup. Now what we need to know is how to set this up, and we'll do it in the lab, in the class. You also need to know the reasons why we've set it up in this way, and what we're trying to do is to make sure we get an accurate value as possible. And we'll talk about that a little bit more in just a second. Now, what might you get asked in an exam situation or test situation about this experimental setup? Normally it's along the lines of, why is your value that you've calculated from your experiment different from the expected energy value when you burn this fuel? Now, there's just some standard replies and responses that you really just need to remember. They could give you a diagram like the one that we just looked at where there was an incorrect setup. Perhaps the thermometer, as I said, is in the wrong place. It's touching the side of the metal beaker and it's not actually measuring the temperature of the water, it's only measuring the temperature of the beaker. That would give us a poor value when calculating the energy released. Something else that could be incorrect, if we think back to that diagram, could be the fact that maybe there's a large gap in between the bottom of the beaker and the top of the flame. Maybe they've got their beaker set up all the way up here, and all the heat energy is just lost because of that incorrect setup. Perhaps they've not got an appropriate beaker. Maybe they're not using a metal beaker for whatever reason. So they're the kind of things that we need to be thinking about if you were asked, why is the value that you've calculated different from the expected value. Some other reasons as well that we should mention: heat loss. If they've not got a heat shield around the experiment, then all your heat energy that you're trying to calculate could be lost to the surroundings and not actually being measured. And also, displayed in that diagram, we've got an orange flame for our methanol when burning it here. Now, an orange flame is indicative of incomplete combustion. If we are incompletely combusting the methanol, we're not getting its full potential in terms of energy. So there's a number of different responses that we could use here, talking about the setup, talking about heat loss to the surroundings, or talking about incomplete combustion. As long as you remember a couple and appreciate the overall setup of the experiment, know what it should look like, then any questions along this line should be quite straightforward for us. Okay, now let's say we've done our experiment and we've collected all the appropriate values. We've got the volume of water used, we've got the temperature increase, we know what fuel we're burning. Now I want to actually figure out, well, how much energy has this fuel released? This is when we need to use this new relationship to us and to calculate the heat energy produced. So on page 3 of our National 5 data booklets, we've got all our relationships for National 5 in terms of our equations, like ones we've seen before, calculating average rate, calculating number of moles, etc. This is the first relationship on that list, EH equals CM delta T. And this is how we would calculate the heat energy produced in the reaction that we've just seen. Now let's go through each part of the equation here, and just to make sure that we're comfortable with what each part stands for and the units associated with it. So EH is quite simply our heat energy. And that's what we're concerned with. We want to know how much heat energy our fuel is producing. Now that is measured in kilojoules, kg. Sometimes it's measured in kilojoules per mole, but that would be more a more higher chemistry. Normally we're just going to be working in kilojoules. The next part of this equation is the C letter. Now C normally in an equation like this is it stands for a constant essentially, and that's exactly what this is. This is a constant value. It's always going to be the exact same value pretty much for all our calculations involving this equation. And C is the specific heat capacity of water. Now it has a value 4.18 kilojoules per kilogram per degrees Celsius. Now don't worry about the units, okay? What we're concerned with is the number. Now thankfully, also on page number 3 in our National 5 data booklets, at the bottom of page 3, it says specific heat capacity of water, and it gives us this value, 4.18. So we don't really need to remember the number. You will, because you'll do enough examples to remember it. But what we really need to remember is that C stands for the specific heat capacity of water. That's measured in kilojoules per kilogram per degrees C. Now essentially, you don't really need to know this, but essentially what it is it's the amount of energy required to increase a kilogram of water by 1 degrees C. So if I had, let's say, a beaker with a kilogram of water in it, how much energy would I need to put into that 1 kilogram of water to increase its temperature by 1 degree C? Well, the answer to that is 4.18 kilojoules. That's what the specific heat capacity of water means. It's the amount of energy required to raise temperature of a kilogram of water by 1 degrees. Now, as I said, that's not really too relevant for us at this point. We are more concerned with the fact that the number C is 4.18. Next part of the equation is M. Now that stands for mass. And mass is measured in kilograms. Make sure that we really do remember that the mass is in kilograms. I'm going to go over that in a little bit more detail in just a second, but mass is definitely measured in kilograms. And this is where people, when they're doing this calculation, will make the most mistakes, is getting the correct mass. And then the last part of the equation, pretty straightforward. Delta T is the change in temperature during the reaction, and that's measured in degrees Celsius. So here's our not a chemical equation, excuse me, here's our mathematical equation that we're going to use in order to calculate the heat energy of a fuel. Now, important point, very, very important point to note here is that every single part of this calculation is all about one thing and one thing only. And if we remember this one thing, or essentially what all these values are concerning, if we remember that every single part of this equation relates to water, it will make our life a whole lot easier. And what do I mean by that? Well, C is the specific heat capacity of water. Mass is the mass of water. Temperature change is the temperature change of the water. So in our experimental setup that we've looked at, what are we measuring? I'm measuring the temperature of the water. I know the mass or the volume of the water, and we also know the specific heat capacity of the water. As long as we keep all that in mind, as long as we keep in mind the fact that everything in this equation is about one thing and one thing only, it's about water, 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 these questions are quite straightforward. Okay, let's look at an example now then. So, question number 1. A spirit burner was filled with ethanol and used to heat a copper can containing 200 centimeters cubed of water. The temperature rise of the water was from 22 degrees to 27 degrees. Calculate the heat energy released from the combustion of ethanol. Okay, perfect. Second, we see this kind of 4-word phrase, calculate the heat energy. I know instantly I need to write down heat energy, EH, equals C times M times delta T. From there, as long as I remember that, the question is pretty straightforward. I need to remember my 3 values. C is the specific heat capacity of water. On page 3 of the data booklet is 4.18. The mass, well, the mass, let's take a little side note over here, is the part, as I said, that most people will get wrong and continue to get wrong. Sometimes they might put in the mass of ethanol up here. Let's just say, take a wee side note, sometimes you get questions where they say the spirit burner was filled with, I don't know, something like 1 gram of ethanol. Now that's a mass. Now most people see that mass and just go, right, okay, that must mean that the mass in this equation is 1. And then the temperature change, well, that's easy, that's 22 to 27, that's a change of 5. And then go ahead and do that equation. That's definitely, definitely, definitely incorrect. Remember what I said before, everything in this equation is all about one thing. It's all about water. Specific heat capacity of water, mass of water, temperature change of the water. So don't get fooled when they put in masses of substances that aren't water. Okay, we will just always remember that everything in this equation is about water. But I read the question through and they've not given me a mass of water. They have given me a volume of water though. So I can calculate the mass of water from that volume. Now it's pretty straightforward, a calculation. If I have 1 centimeter cubed of water, that has a mass of 1 gram. If I have, in this case, 200 centimeters cubed of water, I have a mass of 200 grams. That's a pretty easy conversion. So I say to myself, well, I've got 200 centimeters cubed of water. That means 200 grams, easy peasy. That's my mass, it's 200 times the change in temperature. Well, from 22 to 27, that's a change of 5. And then do the calculation. And I think, well, I've done it. I've beaten the question. Well, no, you forgot one thing. That the mass, as we said before, is always measured not in grams, but in kilograms. So we need to make that final little conversion here to change from grams into kilograms. And in order to do that, I need to divide by 1,000. So 200 grams divided by 1,000 gives me 0.2 kilograms. And that is a little bit of working that we will always have to do for these calculations. You'll see when we do more and more examples, they always give us a volume of water in centimeters cubed. They'll never give you a mass of water. You're expected to be able to say, well, 200 centimeters cubed of water is just 200 grams of water, which is 0.2 kilograms of water. Now, let's put in finally the correct mass of 0.2 for this question. And then our final answer is going to be 4.18 kilojoules. Double underline our final answer. And there we go. I've got 3 marks in my National 5 chemistry exam. Not too bad. Okay, let's just look at one more example to round off the video. Calculate the heat released when burning a fuel that raises the temperature of 100 centimeter cubed of water by 10.5 degrees. So, heat energy equals Cm delta T. We're heating up water, so I'm going to use the specific heat capacity of water, 4.18. The mass of water in this question, well, I've got 100 centimeters cubed, which is the same as 100 grams, which is the same as 0.1 kilograms. So times by 0.1 times by 10.5. 10.5, remember, is the change in temperature. Put all that together and we should get our final answer of 439 kilojoules. Underline the final answer.